And now I believe we are ready to get started. Hello once again. I'm Kitty Jovanovska, Marketing Program Manager at Kumo, and I will be your host today. In this workshop, Arjun Patel, Developer Advocate at Pinecone, and Blaz Stojanovic, Machine Learning Engineer at Kumo, will provide a deep dive into building and deploying advanced recommendation system using fine-tuned embeddings and vector search with Kumo and Pinecone. Thank you, Arjun, and thank you, Blaz, for joining us today. Before we begin, I would like to invite everyone to use the Q&A section, Zoom functionalities, to ask any question throughout the session. At the end, we will dedicate time to answer the most relevant question, and for the one we don't have time to answer live, we will follow up through email. And now I would like to invite Blaz to begin this workshop. Blaz, if you are ready, you can start. Over to you.
Thank you very much, Katie, for the wonderful introduction. It's a big pleasure of mine to be here, especially joined with Arjun as well from Pinecone, to walk you through relational data, how to build models for it, what Kumo does, what Pinecone does, and hopefully we can all enjoy and learn something together. So let me get right into it. Kumo is a company that is built on a very simple premise, and it is that most valuable business data is actually relational. Relational meaning that it is stored in one or more relational tables that live somewhere in your data warehouse and kind of log various bits of information about your business. So here's an example of what this looks like for an e-commerce website, for example, right? So you might store information about your users, products, orders, and views. So the users table might store your users' user IDs, their names, age, of course, all hashed and safe to store. Other static information, where they are, what their preferences are, about your product catalog, so the product IDs, their description, their images, when they became available on your platform and when they stopped being available. And then crucially, you also record event data of user and product interactions, right? So that would be orders, which user ordered which product ID at what time, for what price, and very similarly, which user viewed which product at what time and from which device, for example. And I can go on and on and on. This is just an example for a commerce data set. But for example, if you work for a financial institution, you might have data about users, their loans, their payments, their transactions, etc. And it similarly encodes kind of business-related data that you can then use to build predictive models. Another example is social media, right? There you might have tables up with users, likes, posts, comments, etc., etc. So this is a pattern that is repeated across many industries. And what's even more important is that you can define many interesting problems, many interesting predictive problems on top of this data. So for a financial graph, you might want to predict anti-money laundering or AML detection. You might want to detect fraud and abuse, right? You might want to forecast something about transactions. For an e-commerce or customer data set, you might want to predict customer retention or predict next best action for each user, how to acquire customers, how to retain them, how to personalize and tailor experience for them, which is what we'll be focusing on today, and many more use cases. So the other tenet that Kumo is built on is that modeling and building machine learning models on such data sets is kind of obsolete. So there's a better way to what we've been doing for the past 15 or 20 years, which is kind of the following, right? So you have a team of many data scientists, machine learning engineers, data engineers, etc., which support your very large data infrastructure. They decide on which model to build. And then they start this iterative process of first learning about the data, creating offline features, creating jobs like ETL jobs that produce those offline features, creating the training, validation, and testing set. And once that's built, right, that's when they can start doing actual pre-processing, training, and tuning of models. And for each model iteration, effectively, they have to rebuild these pipelines. For each new feature, a new pipeline has to get built. And this is a very much slow and brittle process, right, that requires many touch points across many different teams, and there are many ways in which it could go wrong. So we've been doing this for 20 years. Hopefully today I'll present a better way to do this to you. But before that, I would quickly like to touch on the specifics of why personalization is so difficult. So personalization is a subset of problems that we can define on relational data that is especially tricky for two reasons, right? One is on the model side, where models need very, very good contextual understanding of both users and items. Usually we want to combine signals from the collaborative filtering side. So that's kind of, oh, this user is similar to these other users because they order the same things or watch the same movies with contextual features, right? So this user is similar to this user because they're of the same age or come from the same place. And our model needs to understand both, and it needs to understand both on the user and item size. But then personalization comes with additional production constraints. So it might be time sensitive, and of course, any solution must meet scalability and other production requirements, which puts additional strain on our already brittle machine learning model building process. So recommendation models today struggle with unifying the signals I described into a single model. So usually you would have multiple components. So you'd have a collaborative filtering component, a deep learning based model to do the content based, and then kind of various mixing approaches to actually build the final multi-staged pipeline that's most commonly follows the same pattern of retrieving items for each user, ranking them, and then re-ranking them with some more contextual real-time information. And any type of inconsistent representations of users and items across these stages necessarily results in worse models, right? So is there a better way? Well, at Kumo, we believe there is. And it's based on a paradigm that we call relational deep learning, which is actually twofold, right? So we need to understand two things to use relational deep learning. First, there's a way to represent any relational database as a relational entity graph, and it's very simple. So we take each row in all of our tables and say there are nodes, right? So if we have a users table, each user row in that users table becomes a user node in our graph. Likewise for the products. So each product that we have in our products table becomes a product in our relational entity graph. We do the same for users and products, users and views, right? And we end with this relational entity graph that we see here on the right. So users might be connected to their view or purchase events, and those events are then connected to the items on the other side, right? So it's kind of a bridge. Each event is a bridge between user and item. And there's many ways to define these graphs. This is just a very simple example, but one that's very relevant for today. And even here, you can begin to notice, like from these graphs, you can elucidate very interesting patterns, right? So you can see which items a user purchased. But then if you continue traversing this graph, you can see which users viewed or purchased that item, right? And kind of by expanding this neighborhood, you get a better and better representation for the user, right? So this building of the graph is the first part. And then the second part is having an actual model um, that can use this graph without throwing any information away to make predictions on various tasks. And those models are graph transformers or relational graph transformers. And Kumo is kind of at the forefront of both developing and productionalizing these models for various use cases. So let's take a look at how they work, right? So the key observation that I've tried to illustrate already is that the subgraph around an entity can be understood as a tree, right? So for example, let's just take one user we want to predict something for. We can connect it to the past orders they've made, the past items they viewed, right? Those item view and item purchase events, we can connect to the actual items, and we can go hop by hop by hop, gathering more and more information at different hop lengths. And this tree we can then sequentialize without any loss of information into a sequence of token, right? A sequence of tokens where the user is the seed token, and then the following token, the follow-up tokens are the first hop interactions, the second hop interactions, and so on and so on. And you can already begin to see that if we also include features of each of these nodes into the sequence, both the contextual and the collaborative signals are captured. And that's what Kumo models do, right? So in particular for personalization, they're able to learn kind of filters, correlations, and aggregations. So they can learn all of these very interesting patterns by shaping data in this way. So for example, they can learn what the last purchase of a user was. They can understand what the last K purchases of a user were, right? They can understand facts within a time range, right? They understand correlational signals, so collaborative signals, like which items are bought together frequently. What are some repeated and regular patterns we see? Um, and then, of course, aggregations as well. I would love to go into much more details here, but for interest of time, this is kind of an illustration of what we're trying to do, and maybe I'll speak more to this when we go through the notebook. And what I would like to really hammer in here is that this type of modeling approach is very similar to what we see in other fields of machine learning recently. And it's kind of moving away from that model-centric approach of building many different models and experimenting with many different features towards a data-centric approach where the machine learning engineer and data scientist ask themselves not what kind of model I can build, but instead, what's a model that I can put as much high-quality data in as possible, right? So then I have a clear way forward by improving the data. So in text or computer vision problems, you start with raw input, which will be text or images. You continue with a natural language prompt or a predictive task defined in some way. The large language model or vision transformer does some common sense in context reasoning and it outputs text. And Kumo parallels this, but for relational data. So you take your whole relational database, you use this kind of lossless conversion into a relational graph. You put it into the graph transformer, you give the graph transformer a relational prompt. Of course, I'll explain in the notebook what this relational prompt looks like. The model does some sort of relational reasoning and outputs prediction and embeddings. And then this is what we're going to be illustrating in the second part of the notebook is how do you actually use those embeddings to build interesting applications, right? So we'll start with relational data. We'll input it into Kumo. Kumo is going to both learn the embedding model and produce the embeddings, which will then output into Pinecone. And that's when Pinecone will do its magic by helping us very easily index and then search and re-rank across those embeddings. So that's kind of the short introduction, short and sweet introduction from my side. You can try Kumo for free by requesting the demo. We have a bunch of example notebooks, including the one we'll be showing today available in our documentation page, so you can learn more. And with that said, I'm handing it off to Arjun. Thank you very much.
Hey everyone, thank you, Blaz. I'm excited to talk about how to use Pinecone with Kumo in order to build these types of recommendation and personalization systems. Whoops, there we go. Can everyone see my slide deck? All
Yes,
right,
we can.
great. So you may have heard of Pinecone already, or maybe you haven't. We are the infrastructure for knowledgeable AI. What that means is whenever you have a lot of embeddings that you might need to store somewhere and do lots of search over, you can use our product, the Pinecone Vector Database. And the key value from using the Pinecone Vector Database is to index these vectors to create fast search and grounded generations. Usually this is within the context of semantic search, so you might have a ton of documents and you have some query and you want to find the documents that are related to that query using Pinecone. In this case, we're using embeddings from Kumo, which we're going to index into Pinecone, and we'll be able to treat them just like any other embedding model. If it were a text embedding model or an image embedding model, we'll do this form of querying and vector search over them to enable these recommendation and these personalization experiences. So how does this actually work? Well, when you have tens of thousands to hundreds of thousands to millions to billions of vectors, you need a really efficient way of partitioning that vector space to enable this sort of fast search. And Pinecone has these proprietary algorithms that allow you to experience this type of search with low latency, fresh data, and very high recall. And the best part is you just need to make a few API calls. You don't have to think about actually deploying the database yourself or doing any of that mechanics yourself. Pinecone takes care of that for you. Like I implied earlier, there's two main ways in which we're going to use Pinecone and Kumo today. The first is going to be to enable this type of similarity search via embeddings from Kumo in an actual demo. So we'll show you what it means to do this type of search within a productionized context. And you'll also use Pinecone to complement the capabilities of Kumo when creating these embeddings to do things like sparse, dense, or re-ranking in your search pipeline or your recommendation pipeline. I want to quickly go over what this actually looks like inside Pinecone so you can see for yourself how easy it is to do. Creating indexes is really straightforward. All you need is the dimension of the embedding model you're using, which you can obtain directly from the embeddings. And you can just call Pinecone to create your index with the embedding dimension and the specification for how you're going to be using the indexes. Querying is also super straightforward, assuming that you have your models embedded already or your data embedded already. All you need to do is pass those queries into Pinecone to get your results back. Depending on what database you're querying and what embedding model you're using on what other piece of data, that determines the functionality here. For example, if you have an index of users and you have user embeddings, then the type of search you'd be enabling is finding users that are similar to the one that you're looking at. Or if you have a lot of items and you're doing item embeddings, you might be looking for items that exhibit similar behaviors to others within your database. And if you want to do some sort of sparse embedding or sparse search, which is really helpful in situations in which you want to complement these embeddings from Kumo with embeddings of the descriptions or the tags or any other unstructured text that you'd like to represent inside Pinecone, you can now do that with our proprietary model, Pinecone Sparse English, which generally tends to beat best match 25 whenever you're doing any sort of embedding here. We're going to show you how to use this model in a hybrid search context later inside the notebook. Cool. That's all I got on the Pinecone side. I think we're ready to jump inside the notebook. Back to Blaz.
Oh, very exciting. Thank you for the wonderful intro. Let me start sharing the notebook. Okay, everybody should be seeing the notebook now. Am I correct, Katie and Arjun? Nice.
Yep.
Okay. Thank you very much. So we're going to be doing this in two parts, right? As I alluded to earlier, there's really two parts to this. First, you got to build your embeddings, and then you can build your applications with your embeddings. So to build or produce the embeddings, we're going to be training a Kumo model, or actually we've pre-trained it in this case just to keep the presentation on the shorter side, but this model actually takes about 10 minutes to run. Nevertheless, we're going to be using the Movie Lens dataset. It contains users, movies, and their ratings. We will be using this data to first build a relational deep learning model that outputs both user and movie embeddings. To build this model, we're going to be leveraging ratings as kind of the crucial event that we want to predict, right? So if we can predict very reliably which movies the user will review next or give ratings to next, then we have kind of a very valuable similarity measure that we can use to model this, right? So let's get started with part one, building a user and movie embedding model in Kumo. So Kumo is available as an SDK API. You can pip install it. You can just pip install Kumo AI. It's very straightforward. If you want to try it for free, we'll give you an environment and an API key, very much similar to Pinecone. So you can give this a go right after this webinar. You can just go to our website and ask for the API key. And what happens is you're gonna get a deployment that you can then connect to with your notebook and start building models, right? So Kumo allows you to connect to data at various locations and sources. So here's just a few examples, kind of if you have relational data stored in Snowflake, Databricks, or Amazon S3, which is going to be the example we go for today. You can connect to that data by creating a Kumo connector. So we can go ahead and create a Kumo S3 connector. We tell it the root directory of where the data is stored in S3. So we're actually hosting this data set for you to try out. So if you want to make a copy of this notebook, you can just run through and this should be all working. For you. Once the connector is built, we can list the table name, so we can find all the tables there. We can then inspect the tables. This is kind of very straightforward thing to expect, which you can expect from connectors. I think it's good to know what data we're actually working with. So it's very simple and dumbed down just for the illustration of building a demo model, but probably the data sets you see day to day can be much more complicated. And of course, Kumo allows for this. So any type of schema you can import into Kumo. Here, for the users, we just have their user IDs. For the movies, we have several IDs. They're the title of each movie, its genres, and its movie poster. And then the ratings are also very simple. So it's kind of the equivalent event of orders from the introduction, where you have the movie ID, the user ID, the rating, and the timestamp, right? And that's enough for us to get started. So the way I described how Kumo works before is 2 steps, right? So first, we have to create a graph which kind of encodes this relational database. And then 2, we have to build a model on top of it, right? So let's get started with the first part, which is building the actual graph. So the graph is built out of Kumo tables, which are just source tables with some additional semantic information. And this is very important because every piece of data in your relational database needs to be vectorized, right? So how we create Kumo tables is we basically point Kumo to an underlying source table, but then we also say, look, this is the primary key, this is the foreign key, this is the time column, and then we also tell Kumo what the semantic type and data type for each column are. And this is actually a very important feature of Kumo because it allows you to play with different encodings of data, which of course is then useful for creating very good models. So it's very simple. We do this for all 3 tables. We have our users, movies, and ratings table. And then we can go ahead and create the graph. So we create the Kumo graph by combining several Kumo tables. The only additional information we need to add is how those tables connect to each other. So in this case, we have the users, movies, and ratings table, and we have an edge going from ratings to movies, to users, sorry, via the foreign key user ID, and we have another edge going from ratings to movies via the foreign key movie ID. And this is what our graph looks like schematically. But under the hood, what happens is Kumo builds a representation I described earlier. So each node, each row in each table becomes a node, and each primary foreign key relationship or connection becomes an actual edge in the graph. And that's actually the first part done. So once you're finished building the graph, you have a data structure on top of which you can build relational graph transformer models. And if you remember the slide I had on the parallels to textual tasks, where you have a text corpus, a prompt, and then the output, right? The next thing we have to do is the prompt, and that prompt is the predictive query. We've kind of designed it to be similar to SQL, but future-looking. And it tells you how the model is defined or what we want the model to learn. Under the hood, it lets you generate the training and prediction tables very efficiently and kind of without touching the graph at all. So here's an example. I'll show other examples as well. This is the one we're actually using to build the model. So we tell the predictive query, look, this is the graph we want to use. Of course, we know which tables are in there, and then we want to predict the following thing. So we want to predict the distinct list of movie IDs a user will rate in the following 14 days, right? And we want to rank the top 25 of those for each user ID, right? So in essence, what our model is predicting at any point in time, in a time frame from today, 14 days into the future, give me the distinct movie IDs for each user ID that we expect high likelihood of interaction. And this is how under the hood we construct the positive and negative examples and train the embedding model. But of course, there's several other queries we can define, just like how you can query or how you can prompt a language model, many things once you have the initial base text there, right? So for example, if we wanted to predict customer churn, we could predict if the count of ratings this user will have in the following 30 days is equal to 0, right? Or we can predict the sum of the ratings of a particular user across a month. Or we could predict how many ratings a particular movie will get in the next following 14 days, like if you want to optimize downstream architecture for serving. And there's countless tasks you can define in this way. The main point I want to illustrate is that this is kind of decoupled from the graph, right? Once you import your relational database, you can define many models using this predictive query. And once this predictive query is defined, that's kind of a declarative statement which defines a machine learning model for you. And Kumo provides you with the necessary infrastructure to actually train this model, right? So to train this model, we generate a training table and launch a training job. Of course, you can specify different parameters here. In this case, we're interested in creating embeddings and we're gonna specify the number of hops. So if you remember the tree that we built for the user to be input into the relational graph transformer, we can shape that tree in different ways. And that's really kind of how modeling is done with Kumo. Once we're happy with the model settings, we can launch the training job. Here, in this case, the training job is already completed. It took like 10 minutes to complete. I think here's an actual example of what it looks like in the Kumo UI. So you see the graph. We have users connected to ratings, ratings connected to movies. We provide users with some stats about the actual underlying graph. We explain how the training table is generated. So we see we have almost 1 million training examples and then about 10,000 validation and holdout examples. And we show kind of all the trials Kumo does under the hood to build the actual model. So you can take a look at the training curves and see if you're satisfied with the model. I think kind of map at 100 is a good metric to see if these models are doing well. And then, of course, once the model is built, you can produce the embeddings for all of the entities, so all of the users and movies that we have in the graph. This notebook contains much more information about how the actual predictive query object works and what kinds of models you can use. So if you're interested, I really do encourage you to take a look. But generating embeddings is very easy as well. You basically, instead of creating a training table, you create a prediction table, you give it to the trainer object, and you can make predictions, or in this case, just the embeddings. So I've gone ahead and done that. It took a few minutes. You can also see this batch prediction in the Kumo UI. So it took 8 minutes and it output 55,000 rows that now Arjun is going to tell you all about how you can make use of. But this is how easy it is to make an embedding model in Kumo. And you can do it for any pair of entities, not just movies and users. You can do it for users and items. You can do it for transactions, etc., etc. The possibilities are really endless because the approach is very general. But alas, we're focusing on personalization today. So let me hand it off to Arjun for the second part, where he will actually take these embeddings and build some applications with them.
All right, thanks so much. Let me go ahead and share my screen so we can just pick up right where you left off. The cool part about Kumo is it kind of takes away a lot of like the manual feature engineering and effort it takes to create these embeddings. And the cool part about Pinecone is that it also takes away a lot of the effort needed to do this type of search over those embeddings. And because we now have all this information of the users and the movies in embedding format, we can use Pinecone as if they were any other sort of embedding. So we're going to go ahead and show you how to now create those applications for personalization and search using Pinecone. First thing we're going to do is install Pinecone and some helper things to make it easier to use Pinecone inside of a notebook. And we'll set our API key with Pinecone, which you can get by signing up for a free account on the Pinecone website. The first thing we're going to do is prepare our data, grab the embeddings we just created, and upsert them into Pinecone into 2 indexes. One for users, which will contain the representations of what the user's behavior are, and one for the movies. And then we can do cool things like finding personalized movie recommendations or finding similar movies given an input target movie. We've already made the embeddings in the first half of this notebook, so we're just going to grab them and go ahead and associate them to the user and the movies data frames. So that's great. We got 5,000 user embeddings and 10,269 movie embeddings. We'll merge them and we can kind of see what these embeddings look like. So we took all of the structured information and now we have a fixed size vector representation of what users look like and a fixed size vector representation of what the movies look like, which is kind of cool. And we can compare them. Now we're going to do upsertion. So we're going to store the embeddings inside an index in Pinecone. Like I said prior, we're going to have a movies index and we're going to have a users index. In order to create indexes, we need to know how big the embeddings are so that we can correctly specify what the index is going to store. And we do that by looking directly at the size of the movie embeddings. And because those are the same as the user embeddings, we can use the same embedding dimension as well. We use create index, specify dot product because that's the nature of the comparison that we're making. And also some other things to specify that we're going to be using the serverless version of Pinecone, which is nice because it allows you to scale up and down based on the number of requests and the amount of information you're storing there. After we create those indexes, we're going to connect them so we can do upsertion. Upsertion is super easy. All of our data is inside a data frame already. We do some transformation to make it easier to understand. There's 3 key fields you need to know about. First is IDs. We're going to use the IDs of the movies and the users respectively. Second is values, which is going to be the embeddings. And third is the metadata. So any additional information about this information we're storing in Pinecone that could be helpful to filter on, for example. So here we're using title, genres, posters, and movie ID that could be additionally helpful to kind of pick up on. There's a helper function on indices called upsert from data frame, which makes it a little easier to do batch parallel upserts. We're going to use that to get everything inside Pinecone. And we can double check and make sure that everything's there. And that's it. We're ready to now work and build these types of applications we've been describing prior. There's a little bit of transformation we have to do in order to make these applications work. The first thing we're going to do is personalize user recommendations. In order to make that work, we need to fetch a user embedding from our index, and then we need to do a search for all similar movies to that user embedding. And this is super easy to do with Pinecone just by using the querying call. We have some helper functions here that Blaz wrote to make it easier to see the results of this embedding search. So what we're going to do is grab the user ID, the ratings data frame, movies data frame, how many results we want to return, and a history variable in order to see the movies that are being returned from this similarity search. So I'll skip over this here because a lot of this is just helpful boilerplate to display these results. We'll pick a user ID and we'll run our display user history and recommendations function. If we go back up here, we can see where we're actually calling Pinecone. It's this one function, query response, movie index query, passing in the user vector, top K, which is the number of results we want to return. In this case, the number of movies we want to return, and then the metadata of those movies. We can see here, when we do that querying, we get the Imitation Game, and we get the Grand Budapest Hotel back, which is pretty cool, pretty interesting. Great. Second thing we're going to do is we did user to movie search. Now we want to enable movie to movie search. And this is helpful if you want to recommend similar movies based on a movie a user has seen already, or you just want to show people related movies when they're searching for them. This is also very straightforward. Instead of querying with the user embedding, we're going to query with a random movie embedding. We're going to follow the same process of kind of picking a random movie embedding and then querying that against Pinecone. We have some helper code here that helps us structure what these results should look like. And I'll go ahead and highlight again the line of code that helps us do this querying, where we're passing in the movie vector this time, the same top K value, and include metadata so that we can get a nice result like this one. We can see our input movie was 3 hearts, and we're getting a bunch of movies that are related behaviorally and contextually to that input movie. Super easy, super cool. The final form of search we want to show off is hybrid search. This is a common design pattern for users at Pinecone that want to leverage the benefits of like a sparse search or any other methodology along with sparse search and combine the results somehow. The example we're going to show off is really simple and could be implemented with other simpler methodologies, but is really instructive for the power of these types of search methods. We're going to try to do a sparse search over genres, which allows people to kind of pick up on the type of movie they want to see. And then we'll reorder those movies based on the actual Kumo embeddings that those movies are being generated. So we're going to combine 2 kinds of search in order to enable this more powerful experience. First thing we're going to do is create that sparse index. This is the model I was discussing prior, Pinecone Sparse English v0. What we're using here is slightly different than what we would normally use for creating an index in Pinecone. We're using something called integrated inference, which allows us to specify a model that's hosted on Pinecone, which means you don't have to worry about hosting that model yourself. You can just call it and create the index inside Pinecone. Next thing we're going to do is use Pinecone inference embed to kind of embed a query and kind of see the result of that here. Then we'll write some functions that'll do this batch embedding so that we can get all of these sparse embeddings inside Pinecone. Once that's ready, we can write some helper functions to do some manual re-ranking for this type of search that we described, where you're going to do a form of sparse search and then re-rank with the dense representations. That's what this function is doing here that Blaz helpfully wrote for us. We can see that we are querying with the sparse candidates. Then after with the sparse candidates, we are filtering our dense query to just those sparse candidates and then conducting another semantic similarity search within those candidates. Then we're going to combine the scores using a weighting function and return the highest ranking scores. This is our final function that kind of cleans up the display, make it nice to look at. We can take in a random user ID, the user ID example, and this is the similarity of what we end up getting. So you can see that this user is kind of looking for sci-fi stuff. And also, not only did we find sci-fi movies, but we found movies that could be contextually relevant for that user with the condition that they are of the sci-fi genre. And that's it. That's how easy it is to use Pinecone and Kumo together to enable these kind of advanced personalization experiences. All right.
Thank you, Blaz, and thank you, Arjun, for sharing your knowledge and practical examples. Now we'll begin with answering questions live. So I would like to invite again everyone to use the Q&A section to submit your question instead of the chat. So this ensures that our speakers can easily see and respond to your questions. So now I invite Blaz to start by answering 1 or 2 questions, followed by Arjun. Blaz, if you are ready, you can start, but please do not forget to read the question before you're providing the answer.
Thanks for the reminder, Katie. Okay, so I'll start. I'll just go top down from the questions that were asked. So Vishal asks, are there any use cases for lead gen? I assume this is lead generation. If it is, yes, then there are. We've actually solved a few of these, actually 2 or 3 now for our different customers. And it works exactly the same way as personalization does. So you bring in your relational data. It might be about your potential leads, about your past leads, your interactions with past leads, or your salesperson interactions with past leads. And then you can predict which of the new leads will be more successful than others, rank them, and then give them back to your salespeople so they can go after the most likely to convert first. So we've seen good success with this. If you're interested in trying, I do recommend signing up for a free trial, and someone from Kumo can help you actually build this model out very quickly. So the second question I'll answer is by Ian. His question is, I'm interested in learning more about how this is creating workflows around the relational database. So much of this rethinks the traditional stack around ETL pipelines, etc. Are you seeing any new stacks emerging from customers using Kumo? Essentially, in what way does shifting to this embedding model change the way we should be thinking about insights from business and customer data? Yeah, this is a very good question. It's very thoughtful about process and how this changes how machine learning and machine learning engineers and data scientists behave. So yes, this does change a lot because many of your ETL pipelines are now not needed anymore. So it shifts those ETL pipelines towards earlier stages. So usually the output of those ETL pipelines would be raw tables that can get inputted into Kumo and a graph can be built on top of. So a very common stack is kind of you have your data collection, then you have ETL jobs which write those to a relational database. Kumo sits on top, and then the output is written into your desired output, usually back into the relational database. Most commonly, if the use case is online, then those outputs get input into a vector database, much like Pinecone, hopefully Pinecone, and then you can use it from there. So I hope this answers your question. Of course, there are many other patterns emerging, but those are very use case specific. But a lot of the time, the whole pipeline gets much shorter. So usually from 5 to 6 steps, you have 2 or 3 steps. Arjun, do you want to take a question or two?
Yeah. If anyone has questions about using Pinecone, please put them in the question and answering section, and I'm more than happy to get to them. The rest of the time for this presentation is just for answering questions. We have a load of time to cover a lot of different topics. There was one that was asked earlier that I'd like to answer. Valentine is asking about other vector databases like AstroDB or Milvis compared to Pinecone. There are a few key things you want to think about. A lot of these databases are open source, which means you will have to deploy them yourselves, which requires a lot of engineering effort. Pinecone is already deployed on our platform, and you can access it via an API or through our partner services like AWS, GCP, so on and so forth. The second thing is the ability to index millions to billions vectors in data. Pinecone uses proprietary algorithms that are more performant at doing so compared to other algorithms like HNSW, which kind of take a long time to rebuild indexes and introduce a lot of latency. And the third thing to kind of consider is our serverless capability. So for some vector databases, you have to allocate pods or GPU, CPU resources to kind of maintain availability for that vector database. With Pinecone, you can just use what you actually use. You get charged for compute and storage separately. So if there's more queries happening on your service, you're going to get charged more. If there aren't as many, you'll get charged less. And also that relates to the storage as well. So if you're storing a lot of data with us, you'll get charged more. If you're storing less data with us, you'll get charged less. And many people find a lot of cost reduction with using that type of service. So these are only some of the reasons as to why you should try Pinecone. I encourage you to try and kind of get started. We do have a free tier. But yeah, those are some things you should think about. I think that covers the Pinecone exclusive questions for now. So I'll throw it back to Blash.
Okay, I have a few rapid fire ones, which are very simple to answer. So let me go ahead with those. So Hadith, I hope I'm pronouncing your name correctly. Question for the first presentation. Why should view have the same field with the orders table? Is not this data redundancy? Is this not data redundancy? Yes, you could view it that way. Still, it's very useful. So first of all, it doesn't have to share the same fields. It might. So it's definitely gonna share the user ID, the movie ID, or the user ID and the product ID and the timestamp, because those just have to be there for connecting those. But then you might connect, like for a view, for example, you might record how long the user spent on that page. But for the order, you might record how much they paid for the product. And vice versa, even for conversions, it makes sense to keep the views because the model can learn which types of views actually convert to conversions as opposed to just views, right? So that's very useful semantic information for the model. Okay, Santosh asks, is it possible for Kumo to automatically extract all the tables and the relationships from the schema? Yes, this is possible. Still, you are required to actually select the tables you want to include. But especially if you're using the UI, for example, the graph can automatically detect primary and foreign key relationships based on kind of column name semantics. Let me see. There's one more question I wanted to answer. By the way, Arjun, if you want to hop in, just give me a ping. So
No
Rahul
problem.
asked, the core purpose of transformation of relational structure to graph is to seamlessly record time order interaction using multi-hop. That's essential for transformer. Yes, your understanding here is correct. So the way we structure data is for two reasons. So firstly, so that we do not lose any information. And secondly, that we can use these powerful models and representations on top of that data. And yes, Kumo can also handle data sources like logs, so textual data, convert them to a graph. And we also allow you to use your own encoder. So if you have text data and you want to encode it in a particular way, you can bring in embedding columns into Kumo and use those. Should I keep going, Katie? Arjun?
We've received a few questions, I think, in the chat. So Arjun,
Yes, I'm taking a look. How is asking about semantic search or search capabilities on top of location-based data using Pinecone. The great thing about Pinecone is that it's really agnostic to the vectors that you're kind of throwing into the database. So no matter the context of the embeddings that you're kind of creating, as long as the query embeddings and the embeddings that are being upserted into Pinecone are designed to be compared against one another, you can enable that sort of capability using our service. So it doesn't matter if it's these types of unstructured, it doesn't matter if these types of complicated embeddings from Kumo, it doesn't matter if it's image embeddings or video embeddings, as long as you can justify the comparison of the query embedding and the document embeddings, or any embeddings that are being stored in Pinecone, you can enable this type of search. That being said, I'm not aware of any location-based embedding models that exist, so I kind of want to ask you to clarify exactly what you mean by that. But as long as you can turn it into an embedding and you want to enable search over that information, you can totally do that. We did get a few questions about the availability of the notebook. I believe the notebook is currently public now, and we'll also share the link directly to the collab either through Pinecone or through email as well.
Yeah. Blaz, you can continue with the question that we received in our question and
Sure.
answer section, please.
So another question by Nobin. Um, First is, could you please share what kind of base model Kumo uses? So the base model of Kumo is proprietary, but you can understand it as a graph transformer. So if you're familiar with the graph transformer literature, you can infer that pretty well. And then the second part, also, by the way, Kumo does have some papers on, particularly for recommendation models. So if you're interested in want to learn in learning the details, you can take a look at the context GNN paper. Second question is, how does Kumo handle more complex relationships? For example, a user uploads their PDFs or other data. Do we run batch prediction process to process that data with more advanced logic? So Kumo is really not focused on pre-processing your data. So some kind of formats are not supported. Kind of PDFs is a very awkward one. There are some open source models you can use to process those into more common data formats, which you can then import into Kumo. And of course, if you have an embedding model for PDFs, you can just bring that in and use with Kumo.
And on that note, really quickly, at Pinecone, we do have a way for you to process PDFs without doing the pre-processing methods yourselves. You can use our assistant offering through the context API to upsert PDFs directly to Pinecone without having to do the pre-processing yourself. And then you could do something like we did at the latter half of the notebook, where you're kind of combining Pinecone search along with Kumo in order to enable whatever experience you're trying to create.
That's really cool. Even I didn't know that about Pinecone. That's actually useful because I don't
Yep.
know how to with PDFs
It
very
does the
well.
chunking and the pre-processing for you, and even some of the query creation too. So really cool.
That's very cool. Okay, thank you, Arjun.
Mhm.
Tushar is asking about the use case of gaming, where users can play games from a catalog of games and they play cyclically. We've actually solved a similar problem for one of our customers, and the predictive task doesn't change too much. You just have to choose what you're trying to predict. So maybe instead of predicting a new rating, you can predict the if an amount of playtime for a user movie pair will be above a certain threshold, right? So you can predict, will Blash play Minecraft for more than an hour in the next week, right? So you can restructure the predictive problem in a way so you can get useful user and game embeddings. I'll take one more for now. I can also take more if there's no Pinecone questions.
Oh,
Ganasham
there's a
asks,
few.
okay, then you can go ahead.
Oh no, it's cool. Here, I'll just answer this one really quickly. Does Vishal is asking, does Kumo and Pinecone offer self-hosted options? We have real-time apps and latency is critical. So for self-hosted embedding models, you can always host any embedding model that you want to use on your own cloud, embed those, and then send those embeddings to Pinecone. That's completely fine. And also, we're available through like AWS, GCP, through those platforms in case you want to build applications within those networks already. Blaz, do you want to answer anything else about this self-hosted option? I believe the training jobs are done on the Kumo platform, right?
Yeah, so Kumo is, we don't provide a self-hosted option. We provide a bring your own cloud option. So there are definitely solutions that we can be made there, that we can make there, but not kind of very much automated out of the box like our SES, Snowflake or Databricks offerings.
I will drop the Pinecone BYOC link as well if you're interested in that, Vishal.
Good. I'll answer the Ganasham question. So the question is, are you seeing use cases in real-time recommendations, especially in conversational AI? Okay, twofold question. Yes, we're seeing use cases in real-time recommendations. Usually for many of those, embeddings are good enough. For conversational AI, I've seen a few uses of Kumo in GraphRag, so that may help you out, right? So, but for real-time and conversational AI together, we've not yet had a use case. But if you have one, please write to Kumo support or get a free trial, and I can help you out getting started.
All right, I'm starting to see the Pinecone messages pop up. Apologies, friends, for
Go for it.
not being
Yeah.
vigilant about the Q&A. All right, Nobin has a question about multilingualism with Pinecone. So yeah, we do have multilingual embedding models that you can use on Pinecone. The one we have is called a multilingual E5 large. I encourage you to check that out. It does support the languages that you're listing, Japanese, Korean, so on and so forth. We have an article on our website that shows how to use these in a cross-lingual and multilingual search fashion. So if that's something you want to do, definitely check it out. Derek is asking about a high dimensionality and scale of property datasets and how Pinecone can optimize indexing and search performance to avoid cursive dimensionality in these scenarios. So this is a really good question. So the cursive dimensionality refers to the difficulty of machine learning models to enable predictions because of increasing number of feature sets, right? So the key here is that the representation that you're learning downstream, if you're doing something with Kumo, is probably high signal enough for you to find things like maybe similar properties, so on and so forth. Maybe Blaz is a little more well positioned to answer exactly how these embeddings are being learned inside those databases. That might be something you have to consider if your data set's really small, in which case the cursive dimensionality problem is more prevalent. But typically for these use cases, your data set's going to be quite large when you're training that embedding model with Kumo. Blaz, you want to correct me or check me on that?
No, I think your answer was spot on. So um, the way Kumo helps with this is our models are kind of heavily self-regularized because in addition to the usual data, you also get all of the connections between the data, right? So instead of just getting the user features, you also get kind of additional data for free, which are all the connections. And that really does help by kind of even inflating those small data sets or imbuing them with additional information. And it does really help here.
Okay, so we've Blaž, we have a new question in our Q&A section. Are you able maybe to pick one or two? Because we have 6 time until the end of our online workshop.
Let me see.
We
I'll try
can
and
few more.
I'm trying to find one which I haven't answered yet. So Sima is asking how does this model work? Is there a paper related to it? There are several papers on graph transformers. Kumo also has a paper on uh, uh, context GNN, which is an architecture designed specifically for providing high quality recommendations. So I encourage you to check that out. Um, um, Then another question by Wen is for user interaction data like click, like, and other signals, what's the best practice to update the Kumo Pinecone embeddings? That's a very good question. So I will work under the assumption that you don't need embeddings for the actual click, like, and other event signals, but you instead need embeddings for kind of more stable entities in the graph. So for example, if you have a user in the graph, their embedding will change based on their clicks, likes, and other real-time signals. So the way to do this is by training a Kumo model. Kumo model is actually fully inductive. What that means is it can be applied to an updated version of the same graph without retraining. So you can just make new embedding for that user and update it in Pinecone. And as far as I'm aware, Pinecone has very good support for actually updating the embeddings in there. Arjun can tell you more about that.
Yeah, you should just be able to upsert over the same user ID. And if you're interested in like some more complicated ways of managing like uh, users that might have multiple embeddings, for example, you can check out our guide on how to manage documents, how to manage RAG documents in Pinecone, which has some good best practices on how to write query strings so that you can use subsets to gather like all the document chunks, for example, or a specific chunk if you want like a longer ID, so on and so forth. That might be helpful to kind of think through.
Actually, I have one more final point here, but when you're designing these types of systems, it's very good to keep in mind how often the embeddings should be updated in the first place. Both because it limits your kind of inference cost on the embedding side, but also the cost associated with upserting and updating those embeddings, right? So if you expect user representations to change very rapidly, then you might want to update those embeddings very frequently. But if your users have kind of more stable interests over time, then maybe kind of weekly or daily is perfectly sufficient. What we've also seen customers do is actually run predictions for only a subset of users, which you can very easily do with Kumo. So you can just make new embeddings for your new users, right? So people who appeared yesterday and update the index, or only create embeddings for users who have had sufficient amounts of interactions in the previous day.
Okay, great. So we have reached the end of our workshop. Thank you all for joining and thank you for your amazing question. I hope you gain valuable insight. Tomorrow, as I mentioned in the chat, we will send you email with the video recording, example notebooks, and free trial links. And if you have any question, you already have my email address. Please reach out to me and I will connect you with our team. So thank you once again and have a